Good morning. My name is Arun Gupta, and today we'll talk about service discovery in container orchestration frameworks. Well, this session could go anywhere from like half an hour to 2 hour long, depending upon the depth that we want to cover. But today we have about 45 minutes. And I'm not intending to cover all the details. I'm going to try to cover the relevant details. The slides, the code for everything of this session are available on GitHub, and I'll share the link. I've been in public speaking for a while, for many years actually now. I talk heavily about containers all around the world. I also talk about Java language itself. I also run the local Silicon Valley Java user group here. So what's the need for service discovery? Let's jump straight in. Now, typically when we build an application using a microservice architecture, we have multiple services that need to discover each other. How do these services discover each other? Well, that's the whole concept of service discovery. So think about my simple web application here. It's a web app. There's a name service and there's a greeter service. And the name service just gives me the name once I give it an ID. And the greeter service gives me a greeting depending upon the time of the day in which locale you are, okay, or which region you are. So essentially, I could run multiple instances of those services. If I'm running them as containers, for example, I could run multiple instances of those. But if you look at a container by itself, the container can go up and down at any point of time. I can't really rely upon the IP address of the container by itself. And so that becomes a problem. If I want to refer to a service, how do I refer the service as? If the IP address keeps changing. So that's where I put a wrapper around the bunch of containers that are offering that as a service. So if there are multiple instances of name running, multiple instances of greeter running, I'll put a service wrapper around it and say, here is my service, and that's how I want to access the service. And then my web app essentially can say, I want to refer to a name service, or I want to refer to a greeter service, or both for that sake. Okay? And then at a given point of time, the service abstraction essentially will do the load balancing for you. It'll pick one of the container's instances and return the reference back to you, and then you can communicate directly with it. In this case, of course, what we're assuming is these are all stateless services. So there is no state associated. So it doesn't matter which instance comes to you, essentially. Okay. Now, when it's typically a 2-hour-long session, then I end up covering all 4 orchestration platforms here. I talk about how service discovery works in Docker. I talk about service discovery in Kubernetes, Amazon ECS, and also Mesosphere. It's a 45-minute session. I don't want to jam in the details so that we go at a fast pace, but I do want to cover at least Docker, Kubernetes, and ECS, and maybe able to answer some questions around Mesosphere, because there is a lot of stuff that I want to show, and I want to show some real code samples as well. So let's get started with Docker, for example, okay? Now, Docker, typically people get confused. Docker means Docker, the container only. Well, that's sort of the typical confusion around. Docker is not just the container itself. Yes, it defines an image format. It defines a runtime format on how you can run a container in an orchestration framework. But what people typically forget is Docker also comes with an orchestration framework built in, which is called as a swarm mode. So if you download Docker, Docker engine, then you can just say initialize the orchestration, and there you go. You can have multiple containers running in there. And what's the need for orchestration as a first fact, essentially? Now imagine you have a cluster of nodes running, okay, like 8 or 10 node cluster running. And now you need to schedule containers on that cluster. Well, first of all, somebody needs to manage that cluster, one. Second is, as the containers are getting scheduled on those containers, on those nodes, somebody needs to figure out this container needs so-and-so resources, and this node has so-and-so resources, and that's a match. And that's how I'm going to do it. Or somebody may have said that I want this container to run explicitly on a node which has so much memory available, so much CPU available. So something above the containers has to manage that show. And that's typically something that is done by orchestration. There are a lot more other things that are done by orchestration. The one aspect that I talked about is called as scheduler aspect. And that's the whole aspect, that we talk about Docker, Kubernetes, and Amazon ECS. Now, once you download Docker, yes, you can download Docker on your desktop. You can create a Docker image. You can run a Docker container. All that works fine on a single host. But then that single host becomes a single point of failure. So then you say, I'm ready. I've done my testing development. And now I'm ready to take it to production. And that's when you look at cloud, basically. Like, hey, I'm looking at AWS, for example. Now, how do you set up Docker on AWS? Well, there is a cloud formation template for that. And in Docker language, that's called as Docker for AWS. Now, if you're familiar with AWS, it's just a cloud formation template, which is basically, from an end user perspective, is a script which says, okay, you want to set up a 4-node cluster. I'm going to set up a VPC for you. I'm going to set up networking, storage, capacity, all of that for you. I'm going to install Docker on all of those 4 nodes, and I'm going to set them up as a cluster. So literally with that one click, you can just follow the dialogues, and it will set up a Docker cluster for you in AWS. It's very well integrated with auto-scaling groups. So essentially, if you think about Docker, you have this concept of a manager and a worker. And manager is primarily for the administrative purpose. Worker is where the containers are run, although the containers can run on manager as well. Now, if you have a manager, few managers, typically odd number of managers, and a few workers. Now, one of the concepts of AWS is auto-scaling groups. So what you can do is you can configure the managers and the workers in auto-scaling groups. And as part of the Docker for AWS CloudFormation template, that is automatically pre-set up for you. So what that means is if a worker node goes down, because of the ASG or auto-scaling group, the node will automatically come back up. So the Docker for AWS CloudFormation template is already integrated with that. And there's one for manager and one for worker. So there are 2 separate auto-scaling groups, and the number of nodes in each can be differently. The traffic routing is done using ELB, or Elastic Load Balancer. And if you are interested in looking at the container logs, that once again is fully integrated with the CloudWatch. That's sort of the language that people are used to in AWS land. Okay, so you can see with CloudFormation, you can easily spin up a Docker cluster in AWS and be fully integrated over there. Now, there is, of course, a CE version, which is a community edition, or an EE version, which is an enterprise edition. The enterprise edition is where you can actually buy commercial support. So let's take a look at it. How does my service can be deployed? I'm looking at, Docker has 2 kinds of services. One is a replicated service, where you take a single service and have multiple replicas of it. And that's the one that we're going to talk about here. So essentially, what I want to do is I want to run a Wildfly server. Wildfly is Red Hat's open source application server, or JBoss. So I'm going to take the JBoss server. I want to run 3 instances of it. So the command that I gave is shown at the bottom here. I'm going to say Docker service create. Now remember, you have created a Docker cluster up in the AWS. You set up SSH tunnel with that Docker cluster. Then you can say, now I've set up the Docker tunnel. I'm going to say Docker service create 3 replicas. I'm going to give the service a name, web in this case, and the Docker image name. So essentially, that image is then downloaded on each host, and it fires up the service. And the beauty of this is, once you say 3 replicas, Docker takes care of it. Hey, you said 3 replicas. If a particular instance of service happens to go down, it'll fire that instance back up. And that's the beauty of it. You said 3, it manages the state for 3. Another good part of Docker is what they call as routing mesh. And essentially here what I'm saying is the only addition is I'm also exposing the service on a port 8080. And see why that is relevant. If you look from the load balancer perspective, the load balancer is host aware. It is not container aware. What that means is if the container is moved from one host to another host, which is quite likely, then how do you configure it that, okay, my container is running not on this one, but on that host? So essentially what you do is in your load balancer, you set up all the hosts. Your client makes a request to load balancer. It can give the request to any of the hosts. And if the container is not running on that host, it will automatically be proxied to a host where the container is running. So from your perspective, essentially, it doesn't matter to you. You just talk to the load balancer will pick a host, and in the worst case, there'll be one additional hop, but that is automatically internally managed by the Docker cluster for you. So this is how sort of a simple service is set up for you in Docker cluster, okay? Now let's take a look at it. How do we set it up, in our Docker cluster if we were to do this for our application? So what I did is essentially, I have 3 services here: my web app service, my name service, my greeter service. Okay, those are my 3 services. Now in those 3 services, I'm running a single container, okay? So what you can see, the dash lines are the service. Inside the service, the Docker terminology is of a task. So a task is essentially a container instance that's running for you. By default, all the IP addresses for a web app, name, greeter service are inside what we call as a Docker stack. And if you were to expose it by giving it a particular port, say 8080 in our case, then particularly if you're running in the Docker for AWS, that'll automatically be front-ended by a ELB for you. So now, essentially what you've done is, your name and greeter service in this case stay internal. Your web app is the one that is exposed externally and is accessible to your client as well. Okay? Let's take a look at my configuration file. And I'm going to open it actually in the browser. Let's see if I can. Yeah.
So when you said sets up ELB, does it set up a load balancer for each of the services or just one?
You have to explicitly say, which service you want to expose publicly, and then accordingly there will be multiple ELBs set up.
But otherwise, does it set up ELB for private services as well?
No. But that's the internal Docker concept. The question is that does it set up multiple ELBs or single ELB? In this case, I set up explicitly an ELB for exposing service publicly, but for otherwise, the service itself acts as a load balancer. If you scale the service up, the number of replicas up, that will act as a load balancer by itself. All right, so here we are. This is service discovery here, essentially. So let me look at the Docker part of it. Okay. Now, this is sort of how my service is set up here as I talked about it. Now, I'm walking you through, just an image snapshot of how will I create a cluster on AWS. So essentially, I'm not using it showing the online version, but this is my local workspace. But this is fully in sync with the GitHub version. So I'm setting up a Docker cluster here. I'm selecting a template. I'm specifying the number of managers and the number of worker nodes that I need to set up. I set up my key that I need to be used. Then some other properties, the instance types. And then I say, okay, create my Docker cluster. And once the cluster is created, it's a CloudFormation template. Then I connect to the Docker manager, essentially, and it says how it needs to be done. Then I get more details about the cluster, and then I deploy my application. Okay? So let's see what the deployment really means in that sense. So if I look at my config, let me open up a new tab here. So if I look at config here is my Docker compose file. First of all, the version is 3, and that's the latest Docker compose file version. Then in there, I'm defining services. So first one is a greeter service. Then there's a name service. And I'm giving the tag build here because essentially what it is looking at is the directory, which is /services/greeter, that is going to take that and it's going to build my Docker image for that particular service. And I'm giving it the image name. So it's building the image name here as well. Similarly, I'm building my name service as well. And then I'm saying my web app service. Now, in the web app service, the build and the image tag are exactly alike. And as you can see, all I'm doing is just exposing this service on port 80 on the host to port 8080 on the container. Now, in the Docker compose file, I'm saying depends on. Essentially what that means is the service depends upon these two services. That means those two containers should be fired up before this container is fired up. Container gets fired up, but the application within the container, is that up or not? Is that still application developer's responsibility? That's a key part to understand. And how do really service discovery work in this case? Essentially, there are 6 environment variables that you need to be aware of. So in this case, for example, I'm using name service, host port path, and greeter service, host port and path. And whatever values do I give to that particular variables, those variables are then used in my Node.js code, which is essentially a very simple, tiny web application service. It reads those values and connects to that service. So it's as simple as that. But the key part here that you want to understand is the service name that I've given here is, like in this case, is name service, is the exactly same name as this. And similarly, the greeter service that I've given is the same as the greeter service. And if I look at the service definition itself, Then in the image itself, the Docker file for it, if I look for it, so if I go to say images, no, not these images, services actually, and I look at my greeter service and I look at the Docker file here. In the Docker file, I'm exposing port 8080. Okay, so now if I go back to my Docker compose file, all I'm doing is just talk to the port 8080. That port 8080 is within my Docker stack, but the only port that is exposed is port 80 for the web service. So that's the important part to understand. See how the services are able to talk to each other within the application, yet not be exposed externally. So in short, I'm using my name service. Well, this is a typo. Should be name service to name service, not name to greeter service. And then greeter service to greeter service. So the service names are the ones that matter, and then accordingly you can expose the ports also if you need to. All right, switch gears. Let's talk about Kubernetes now. So Kubernetes is an open source orchestration system for containers, just like Docker here, essentially. Pretty much all the Kubernetes deployments that I've seen so far, I've seen quite a bit of those, they're all using Docker as a runtime format. All the Kubernetes claims that, hey, we are container agnostic, RKT, OCI, other container formats will work for us as well. It essentially was created by Google and donated to CNCF, or Cloud Native Computing Foundation. So it's done in a very, very transparent way, and I'm very actively involved with the community as well. Well, I mean, there are people who are far more actively involved, but I do monitor it quite closely. Just like Docker, it provides declarative primitives for your desired state. So you can say, I want to run 4 instances of this particular service. So it'll keep running 4 instances. If an instance goes down, it'll bring it back up. So that's the self-healing nature of it. It gives you horizontal scaling. You can add more nodes to the cluster very well. And as a matter of fact, one of the tests that they do as part of a Kubernetes cycle is be able to run up to a 5,000 node cluster as part of Kubernetes itself. So if you're really running that big a cluster, let's talk about your application architecture itself. It automatically does bin packing, so the scheduler algorithm is pretty efficient in that sense, and there are ways by which you can influence that scheduler algorithm as well. And of course, the aspect that we're going to talk about today is service discovery and load balancing. So let's talk about some basic Kubernetes concepts first. And just like Docker, in Kubernetes, there is a concept of a master and a worker. These are essentially VMs or physical machines or nodes, so to say, where your administration control plane is running. So in this case, of course, in master, I have an API server. API server is nothing but a REST API server, which is listening for your request and responding back to it. And of course, when it's listening for it, it does some actions based upon it. And the actions could be, hey, talk to scheduler and schedule this pod or the container somewhere on the master workers. Now, in case of Kubernetes, the containers get scheduled explicitly on workers only. There is no container scheduled on master, unlike Docker. There's a controller manager as well. The controller manager plays a role that, okay, you're running 4 instances of this particular service, or if an instance goes down, so controller manager keeps an eye on that. And etcd is basically a distributed watchable registry where all the services, all the containers, all the metadata, all the persistent state of the cluster is stored, okay? Now, the easy way, that's the way in Docker, there is a Docker CLI, where you say Docker create service. Here, there is a kubectl CLI. And the kubectl CLI, you give it a configuration file and say, take this configuration file and create my resource. On the master, on the worker side, you have, like in this example, you have 2 worker nodes. Of course, you have your Docker host that's running, because that's going to understand your Docker containers. On the Docker containers itself, on the Docker host itself, you have pods running. And we'll talk about pods in a second. But essentially, pods is the lowest abstraction unit. They don't talk in terms of containers. They talk in terms of pods. You have kubelet running, which is sort of the node agent, which is what the master talks to in order to deploy the pods. And there's a proxy, which basically acts as a proxy to the node pods running on the host. So the master talks to the kubelet. Kubelet then deploys the pod, and proxy gives us a front end for your different pods running on the host. On the client side, like when the client is trying to access the application, your request comes in through internet. to a load balancer, and then it goes into the different proxy, and it says, okay, give me the request back. So the middle part, what I show you here, is called as is the Kubernetes cluster, essentially your master, your workers, and you can set it up in a very similar way as the Docker has shown. And then, of course, there is a kubectl where is the application developer, and on the far right, what you see is sort of your client application. Let's see. Yeah.
Question for you. Are you going to be making the presentation available to us?
It is available already. Okay. Yeah, it's on my GitHub, and I'll share the link. Okay. Absolutely. So all the slides, all the code that I'm showing here is on my GitHub repo. Absolutely. Let's see how this works in terms of Kubernetes. Kubernetes, once again, we have this concept of a pod, as I said. Pod is the lowest abstraction unit. So if you want to run a container, you essentially say, hey, I'm going to run a pod, and in a pod, I'm going to run a container, and the pod has a spec, and in the spec, there is a container. You could have multiple containers running in it, but typically, a pod and a container is a good analogy, essentially, okay? Now, if you want to run multiple instances of pod, then you run a replica set. So you're going to say, I'm going to run a replica set. Replica set is just a developer concept in Kubernetes. I'm going to running a replica set, and that replica set need to scale from 1 to 4 instances. That means 4 instances of a pod are running. Now, each pod in Kubernetes is assigned an IP address, but that if the pod dies on a host, it could come up on a different host and be assigned a completely different IP address. So once again, as we discussed earlier, you cannot rely upon the IP address of a pod. So then what you do is you wrap the pods or the replica set, so to say, in a service. And that's exactly where the role of etcd kicks in. So essentially what happens is you are firing up a pod. To the pod, you assign certain labels, metadata, so to say. And then to the service, you say, hey, you know what? Whenever any pod comes up with that metadata, make that pod as part of me. And that's where your etcd distributed watchable registry comes in. Pod comes up, that metadata goes into the etcd, service comes up, and it says, hey, does any pod have that metadata? Okay, they're part of me. And then now imagine your replica set going up and down. So your service is the front end. You talk to the service, and your number of replicas of the pods can go up and down, and service will still be able to kind of give you an instance of a pod where you can directly talk to it. So in this case, for example, what I'm doing is, well, one more thing. Each concept that I talked about, pod, service, replica, if they have an IP address, that is completely internal to Kubernetes cluster. So if you were to expose it, you have to explicitly expose it. So in this case, for example, web app, name, and greeter are 3 services. Well, think about this. They are a replica set with 1 pod instance wrapped around a service. So the orange box is the pod, then the dashed line is a replica set, and then the very tiny dashed line or the closed dashed line is the service. So that's sort of how you're running it. And again, once again, the web app and the web app is accessing the name and the greeter using the service names essentially. And as I said, all of these objects have a private IP address, but if I were to expose it, I will create an ingress load balancer, saying, hey, you know what? I'm creating an ingress load balancer, and the way you can do that is by simply specifying an attribute in the service description, and I'll show you how that service attribute look like. Well, actually, right about here. So let's look at the source code here. So here is my Kubernetes configuration file. Now, as I said, when I create an application in Kubernetes, I need to give it a configuration file. I need to say that in my configuration file, what are the resources that needs to be created? Once the configuration file is created, then I'll say kubectl create. Here is a resource file example, and then it'll create it. So in this resource file, I got multiple resources. Each resource is essentially separated by 3 dashes here, okay? Now, before I look at the service, let's look at my name pod here, okay? So this is my replica set, and here is the metadata that is assigned to it. So it says name rs. Then I'm saying in the spec, I'm saying create 1 replica, and in that replica, again, I'm assigning certain metadata. Now this is the metadata for the replica set itself, as part of the replica set, when my pod is created, this is the metadata or the labels, so to say, that are associated with each pod. And labels is nothing but just a name value. So I can just pick any random name value here. So in this case, I'm saying app:name pod. That's the value that I have chosen. You could choose completely something that is specific to your application. And then this is the replica set spec. This is the pod in the replica set spec. And the pod says basically, I'm going to have containers. Container will have this name. Here is the image name. And here's the container port. Okay. Now, see this label, app name pod, that is assigned to each pod. When I'm defining my service up here, in that I'm saying, okay, service, this is the kind service. And I'm saying selector is app name pod. So now, when I'm increasing or downcreasing, so to say, of my replica set, if I'm upscaling and downscaling the number of pods in my replica set, they each are assigned that label, and that label is essentially what becomes as part of the service. So if you were to scale your service up and down, you will just scale the number of replica sets or the number of instances of replica set. So that's my name service here. Very similar to that is greeter service here essentially. So I'm saying metadata name greeter service, selector is app greeter pod. If I go down here, this is my greeter replica set. This is my greeter replica set metadata. Within that, I have a spec, one replica, and here is a pod replica. That's the one that is associated here in my app or my service. And everything else is same, okay? Now, if I go down further, here is my web service or web app service. So again, the metadata of the service first. Then I have a selector. That is very similar. Now, in this case, the port I'm exposing is 80. And just the fact that I'm saying type as load balancer, when this service is now deployed in a cloud provider, it'll figure out whatever the cloud's native load balancer is, and it'll expose the service using that. So for example, if you were doing this in AWS, it'll automatically front-end an ELB for you, for example. So that's the way to understand it. And if I keep going down here, here is my pod metadata. That is the one that is being used by the service here. And similarly, I got 6 environment variables: name service, host port and path, and greeter service, host port and path, on how the service will be resolved. And if I look at the name of the service, it says name service, which is basically the name that I've given over here. So it's very similar to the way it was done for Docker. It's just that you have to understand the different terminologies. Now, the good thing about this is it's a very good starting point for you if you want to build a microservice-based architecture, because the code is all here, and you can understand, how the 3 different architecture, how at least the 2 architectures that we have talked about so far are different, and their terminologies are different. Yeah.
The orchestrator or the Kubernetes orchestrator monitors the status and availability of the services?
Yeah, the question is, Kubernetes monitors the availability of the service. It does not monitor the availability of the service. You can add health check for the pod, for example, because it has no way to understand if service is up or not, because services, there is no such concept as service is up or not. The pods in the service need to be up or not, and for those pods, you can add health checks very easily. So in the configuration file itself, you can say, ping this pod every 3 seconds, and if this REST endpoint is not giving me 200, break it down. So essentially what the Kubernetes will do is, in that case, it will shut down the pod, and the moment it shuts down the pod, it says, oh, replica set needs to have 4 instances. It'll try to fire up a pod somewhere else automatically.
But it's handled by the orchestrator?
Yeah. Kubernetes takes care of that.
By other monitoring?
There is no third-party software required essentially for this. That's an inbuilt facility both in Kubernetes and in Docker as well. And that's the whole concept of, you say Docker create service, 3 replicas, it's self-healing. Yeah, but there is a complex scheduler algorithm over there. So for example, in case of Kubernetes, it kind of, in case of Docker as well, let's say you set up a cluster across multiple availability zones, then it'll start looking at it. Well, first of all, it needs to understand what is your pod requirement or your container requirement. Once it figures that part of it out, then it'll say, okay, let me see what is available in the cluster essentially. Then it'll see which of the nodes in the cluster is least loaded. So it's an algorithm one by one. Once it figures out, okay, here are 3 nodes that meet the criteria where the pod can be deployed, then it'll randomly pick one.
But if one node keeps having issues, like, I mean, there's an I/O issue, or one of the disks on the host server is bad, brings up a pod dies, brings it up again, dies. I mean, you get into that state.
So it's less likely it'll keep scheduling it back on the same node. That's my feeling. That's at least what I've seen so far. So it does do that randomization a little bit more. I'll take one more question over there.
How is traffic routed from the service to like the app servers or the replica set? Is there load balancing options or the proxy?
In the service itself, yes. Yeah, in the service itself acts as a load balancer. So just for fun, for example, try to create a pod and that returns a unique IP address of the pod and play with it. That, how often, how does the load balancing work? But typically what I've seen is in the service itself is a round robin load balancing. Okay. Yeah. We have 15 more minutes. I want to cover content. Last question. In this case, I'm still asking for one replica. On the last one here, no, it's still one replica. So if I look at it here, it's still one replica.
So you say that load balancer, so it has to be 2 or more, or?
Doesn't matter, right? I mean, if it's the fact that it is front-ended by a load balancer is completely independent of the fact how many instances are running behind the scene, right? I mean, if it's one, it'll keep going back to that same one. And you want to keep it independent. If you are spinning up more instances, it'll automatically start redirecting accordingly. So again, once again, through animation, we are showing how the services are linked with each other. Now, one of the things that I wanted to do when I built this code was I essentially wanted to keep the service exactly same. So I figured out what are sort of going to be my interception points, and that's where those name service host port and path and greeter service host port and path are there. So the service is absolutely untouched across these orchestration frameworks, just that to give a better feel that here is a common base layer and how do these orchestration frameworks behave. Amazon ECS. So Amazon has a EC2 container service, and essentially it's a fully managed container service. The good thing about Docker and Kubernetes is it's easy to get started. You can do the local development experience, and then you can say, now I'm ready to go production. And then you go on AWS and you say, okay, I'm ready to deploy the service. Now, managing those clusters, if the cluster goes down, if a node goes down, if a node goes rogue, how do I expand the cluster? I'm running on AWS. I want to make sure I attach an IAM role to a pod. How do I do all those things? Those things are not easy, not certainly very easy to begin with. It gets very nasty very quickly. That's where Amazon EC2 container service comes in very handy. It's a fully managed container service on using EC2 instances. There is no need to install, operate. You just go to the AWS console and you say, build my infrastructure. And then you say, I want a 4-node cluster. It'll create the cluster for you. It'll have all the nodes set up for you. It is, again, fully integrated with AWS. So, for example, you can set up CloudWatch alarms. Based upon those CloudWatch alarms, let's say you realize a node capacity is going up to 80%. Based upon that alarm, you can automatically scale your cluster up, or you can scale your cluster down. Hey, node capacity is to 20%, scale my cluster down. So that makes it really easy for you to use the AWS infrastructure and be able to scale your cluster up and scale your cluster down. Now remember, there are 2 things. One is the cluster itself. The second is the one that we were talking about earlier, was application scaling. That is more at the application level. Of course, it is designed to use with lots of other AWS services. So whether it's ELB, VPC, CloudWatch, IAM roles, one of the unique things about EC2 container service is how you can attach an IAM role to a task. The language here is, instead of pod, is a task. That when I'm running this task, assume this IAM role, and will run on that particular node using that role. Here's a quick diagram from the ECS developer guide here, essentially. So what I'm showing is ECS cluster. So you can see those 3 orange boxes on the top and 3 orange boxes on the bottom. That's a 6-node cluster set up across 2 availability zones. So you can do those kind of elaborate facts very easily using the ECS console. Of course, there's a CLI as well that you can use it over there. And essentially, when the cluster is ready, when you're deploying an application, then you say, here is my task definition, which is nothing but a JSON file. You take that task definition and you say, go deploy that task definition, and then you can expose it as a service if you need to, okay? The link to the ECS developer guide is over here. Let's see, how did we do the exact same thing, our web app greeter and name service as part of EC2 container service. Now here, I of course have a name service and a greeter service at the bottom, and those are sort of my task definitions. Just like Docker container pods, here I am running tasks. That's the terminology for EC2 container service. Now that task is surrounded by a service. You can expose it as a service. Now there is another layer of abstraction here called as target group. Now in a target group, I can define, that's sort of my metadata association. I'm saying I want to target something to a particular target group. In a target group, I could have multiple services if I need to. So essentially what I'm doing is I'm defining two target groups here, saying here is my target group with one service, here is a target group with another service. Now the advantage of that is instead of using ELB, I can use something called as ALB, or application load balancer. One of the questions asked earlier was, if I were to expose all three services, they would be exposed by three different ELBs. ELBs could be expensive. And that's where the concept of ALB kicks in. So now I have an application load balancer, single application load balancer. A request comes into the application load balancer. Based upon the path that you are asking, I can make a request to a target group from the single ALB. So as opposed to using ELB. Yes, you can use ELB if you want to use it, classic ELB. That can absolutely work. But ALB kind of gives you that efficiency, and that's why the additional metadata done using a target group comes in very handy. And in this case, what I'm doing is, instead of setting one ALB, by default, all the services are available. So what I'm setting up is an internal ALB and an external ALB, because I don't want the name and the greeter service to be available externally. So I'm just going to set up a load balancer over there so that now I can just do a single ALB, single internal ALB, and talk to those services based upon the path. Because from the web app, essentially, I'm saying, okay, go talk to this path, and then the routing will happen at the ALB level. So here what I'm showing you is how my target groups are created. In this case, you can see there is a greeter target group, name target group, and the web app target group. And in the target, for each target group, for example, you can see what is my target. And I'm defining the EC2 instance, or the EC2 cluster where I should be targeting, essentially. One of the key parts that I want to talk about here, once again, is how my web app service is configured. Once again, I got both name, service, host port and path, and greeter service, host port and path. Those are my 6 environment variables by which the configuration happens. And you can see for the host, which is basically the first and the fourth environment variable on the right screen, we're using the internal ALB IP address. And then, of course, my name and or the path and the port are published over there. So let's look at the code for this one here then. So here is my DCOS name.json. This is my simple JSON file, which is basically the configuration over here. I'm saying this is available at path name, or this is actually the ID, not the path, essentially. It's using a Docker container. I'm giving it the CPU and the memory. Then I'm giving the same image name. And here is the container port, and here is a service port if this were to be exposed as part of a service. Now remember, this service can have multiple instances of this task running, and that is perfectly okay. And here I'm specifically saying the HA proxy group is internal, okay? And we'll see that how it's being used. So that's my name service. Let's look at the greeter service here. Once again, greeter service is very similar. It's got an ID here, got the CPU and the memory here. It's a Docker container, single instance. I give it the image name, and I give it my port mapping, and here the service port is just 10,000 as opposed to 10,001. So these two services essentially are available at two different ports. And then when I'm accessing it from my web app service, I can say 10,000 is the service port available internally. It could be mapped to a port externally, or to my internal ALB, essentially. And this is also my internal service group or HA proxy group. Let's look at the DCOS web app. Now here, once again, ID, CPU, memory, number of instances, container type Docker, same image, and this is the web app one. I'm giving it a port once again. And here are once again my 6 environment variables in this case. So this is the internal ALB. Oh, sorry, this is the DCOS. What am I doing here? I'm showing the wrong configuration files here. Sorry, my bad. I've been talking about DCOS all along. Okay, here you go. So sorry, this makes more sense now. This is the cluster creation for ECS. I got my EC2 instance here. I got my number of instances. I got my storage here. I can create my VPC roles here. And here I'm creating my target group. So I'm saying name target group, and I'm exposing at port 80 here. And this is my greeted target group. I'm exposing at port 80 here as well. Okay. So the target group for web app is created. So all the target groups are created. Now when you are creating an application load balancer, you can say whether you want an internal load balancer or an external load balancer. Remember our internal load balancer from the name and the greeter service? So I'm going to make an internal load balancer. It's spanned over multiple availability zones. I can configure the routing here. Okay. This is where I'm doing the whole path-based routing essentially. So I'm saying if path is greeter service, target to greeter target group. If path is name service, forward to name greeter group or name target group. Okay, that's my path-based routing. Then here is my web app application here. It shows just the routing. It's just taking a standard application in, and it just talks to the one single target group, and that's good enough for me. And of course, I need to enable the traffic here, so I'm just poking holes in the firewall. Then I'm adding my task definition. So here is my name container. I give it the image name, 1024 as a memory limit. Here is my container mapping. The moment I say 0, it'll dynamically assign a port to that particular service. My greeter container here now. And here's a web app container. And the web app container, again, I'm defining all the environment variables. You create the task definition, and then you go on and create the task service, essentially. So once the services are created, I'm going to skip through this here. Well, of course, it just talks about deletion of the services. So I'm going to just skip to the last slide here. Well, at least you got a fragment for the DCOS configuration files as well. So Docker, ECS, Kubernetes, at least those 3 frameworks is what we covered today. The entire code for the services, as I talked about, is available on my GitHub repo. And the slides that I used today are also available on the GitHub repo. Container service discovery is the URL, essentially. So feel free to use it anyway. And if I can take 1 more minute, essentially here, what I'll do is I will go here. And if I can go to services here, I can pick up a greeter service here. I can pick up just, say, actually web app service. That's a good one. So you can see this is my entire service code. It's very simple, nothing fancy here. All I'm doing is I'm just picking up the greeter service host, port, path. Once again, name service host, port, and path. And I'm just returning a response back here. So I wanted to show you the touch points if you were to build service discovery in here. If you were to use it in different container orchestration frameworks, how these services would be able to talk to each other. Now, one of the ways that I've been thinking of upgrading my session is, or adding more details to my session is particularly looking at Istio and Envoy and Linkerd. Those are sort of the new service mesh frameworks that are becoming more and more prominent. So I'm planning to play with that more, hopefully in the next few days, and then be able to, if you're interested in that detail, I'm going to be updating my GitHub repo with that as well in the coming days as well. I think that's about the wrap we have. Thank you.